In our last lecture, we were looking at the structure of the atom, and we have now talked about the fact that we went from first discovering the electron as a subatomic particle, and then moving on to a model that talked about the positive part of the atom, which initially was proposed as a plum pudding, but then verified through experimentation, through alpha particle scattering, that in fact the positive charge and most of the mass of the atom exists in this very small center called a nucleus, a very, very small part of the atom. So basically at this point then, what we are saying is that we have an atom that apparently has a certain overall volume, and in the center of this atom is the nucleus, and the rest of the atom is primarily then empty space. Within this empty space then would be the electrons of the atom. The question was, where are these electrons? How can we predict their behavior? How can we predict their energy, etc.? And so that's the next step in the road of understanding then chemical change and chemical reactions. Well, initially it was thought that, in fact, that if the electrons did exist like this, they should be able to have any energy state. In other words, if we would to take just one particular electron, again we go with the nucleus here, if we were to take one particular electron, it might be here, or it might be in here, it might be out there, it might be moving around. Now, as electrons change position, in other words, as if it were spiraling slowly towards the nucleus, it would be giving off energy. Or if it were spiraling out away from the nucleus, it would be absorbing energy. It would be changing energy because of the attractive force of the electron to the nucleus. And so if we're pulling it out, we have to put energy in to overcome the attraction. If it's moving inward, it is lowering itself in energy. It is becoming more influenced by the opposite charge, and energy would be given off. And of course, this we then now understand is what accounted for the so-called rays, the glowing energy in the gas discharge tubes, is the fact that electrons are changing energy positions within the atom, absorbing and transmitting energy back and forth. Now, as I say, initially then it was thought, from at least a classical physics standpoint, that electrons should be able to have any energy position within the atom. And if that were the case, we should get then all frequencies, all possible frequencies of radiation given off by electrons as they moved about in the atom. And when the early atomic scientists looked at the radiation, the electromagnetic radiation given off by gases in gas discharge tubes, by these cathodes when we ionized them up and had the cathode ray, what they found was in fact that we did see a rainbow effect of the colors. In other words, if we were to take the light from one of the light bulbs in this room, a tungsten light bulb, pass it through a prism, so we split the frequencies up into their individual areas, we would get something that would look like the bottom row. We would get a rainbow appearance. This, of course, is what a rainbow is in nature, is merely the diffraction of sunlight at a correct angle through the moisture in the air, acts as little prisms and splits the electromagnetic radiation. So normally we see the light as the combination of all of it, which we call white light. or in the case of the rainbow, it's being spread out by the moisture in the air, acting as little prisms. And then we see the rainbow. Well, this, of course, fit exactly what they thought, that electrons should be able to have any energy, therefore we should be able to have all frequencies of electromagnetic radiation within an atom. So the first experimental evidence that they had looked, in fact, like it met that criteria, that we were going to have, I guess, what we would call a continuum of radiation. So that it starts at one point, it goes all the way through all. Now this is a blow-up, of course, of just this very small little part that's occurring due to electrons called the visible spectrum. Notice that's only a very, very small part of all this electromagnetic radiation. We talked a little bit about the one. If we go up here, we see a term gamma ray. We talked about gamma ray relative to nuclear change. When a nucleus undergoes change, when it breaks apart and reorganizes, it can give off gamma rays. Cobalt-60 I mentioned in a previous lecture to be used for cancer treatment. When cobalt-60's nuclei then undergo natural radioactive decay, one of the things they give off are gamma rays. Well, we see gamma rays, this is the very high energy of radiation. Down here we have the very low energy, TV and FM and AM radio. So visible is only a very small part of this whole electromagnetic spectrum, but this is the part that we're really looking at right here. Visible, maybe a little bit of the near ultraviolet and near infrared that has to do with the electrons in the atom. The other energies have to do with other relationships within molecules, bonds, etc., that are changing. Rotation of molecules. These account for some of the other energies. And we see even here is one that we're probably quite familiar with, microwaves, which of course we use microwaves then to heat food, and we do this by changing the rotation of water molecules. That's the interaction that we have of the microwave with the thing we're heating. If something doesn't have moisture in it, it's very difficult to use microwave to heat it. Water molecules or water-like molecules are most affected by microwaves. Well, again, as I said then, looking at the light given off, first of all by something like a tungsten light or the sunlight itself, looked like we had all of these frequencies existing in atoms. However, a German scientist by the name of Bohr began exploring individual gases and set up then an instrument that looked like the following. Here it's showing specifically a tube, a gas discharge tube. Now this is different than what Thomson was using. Remember, Thomson was using a vacuum tube. So he was looking at electrons. Bohr is looking at how electrons are interacting with the gaseous atoms that are in there, the hydrogen atoms or the hydrogen molecules. Well, if we put a tube with hydrogen in it, first of all, if we were to look at it with our visible eye, it would look slightly blue in color. When we take the light, pass it, first of all, through slits, that's just to get a nice sharp beam, then let it strike a prism, and it's separated into its individual frequencies now. Instead of getting a total rainbow, what Bohr noticed was that there were only a very few specific lines, very few specific frequencies of energy in that hydrogen atom. Notice here that we have 3, 4, 5, 6, 7, 8, 9 individual wavelengths or frequencies of radiation given off by the hydrogen, in contrast to what was suspected should happen, this rainbow. the rainbow didn't show up. Only a very, very few of all of those colors that we have up there, all of those frequencies, only a few of them actually showed up in the hydrogen atom. Well, let's go back and think what a hydrogen atom is, and then let's come back to this once again. A hydrogen atom is, as I was showing here, a nucleus containing one proton and one electron. The atomic number of hydrogen is 1, telling us that it has one proton. And if it's a neutral atom, it must have one electron. So we have a proton and one electron. Now, as I say, the classical physics idea at that time was that electron in a hydrogen atom should be able to be anywhere. Energy-wise, if it could be anywhere, we should end up with a rainbow of energy given off. But in fact, what Bohr's picture was showing, what the experimental evidence was showing, was that the electron apparently could only be in certain energy positions, not all of them. Why? Why could it only be in certain energy positions? Well, Bohr didn't try to explain why. Bohr only said, this is the experimental evidence. Now we need to build a model that explains this. We must accept the fact that electrons cannot exist in all energy states. Now, it isn't just hydrogen. He looked at many other gases and found the same type of thing, that each element had only a certain number of frequencies of radiation that it gave off. So Bohr said, first of all, we must accept this. This is evidence to show that they don't exist. It didn't make any difference. We could take hydrogen from any place. We could do it many, many times over and over and over. We always got the same result. If we took helium, atomic number 2, put it in a gas discharge tube, looked at it only had a few lines. I think helium only has like 6 lines, 6 frequencies of energy, and yet it has 2 electrons. So Bohr said, number 1 is we must accept the fact that there are certain, what he called, stationary states. That's energy-wise. There are certain stationary energy states within an atom for its particular electron or electrons. And once we've accepted that, then we can go on and begin building a model to try to predict what other elements should look like and to understand then the behavior of electrons in atoms. But that's a real major change in philosophy, and one had to merely accept the fact that this is the way it is. There's no logical explanation for it. So Bohr accepted it. He wasn't real popular, by the way. Initially, it took many years before Bohr was really given the appropriate recognition for his statement of the stationary states, or we sometimes also call it quantized energy. Quantized meaning small bundles or units, so a very quantitative amount for each position the electron can have. Now, to give you a mental comparison of what Bohr is saying versus what the rainbow is saying, classical physics at that time would have said that if I were the electron and this room here we had an inclined plane from here to the top, I could be at any position energy-wise as I go up my potential energy changes. I could be at any energy position from here to up there. That's fine. But Bohr is saying, no, that's not the way it is, and it's not the way it is here. You see, if I am going to change my energy positions in this room, now I can be here, and I can be here, I can be here, but I can't be anywhere in between either one of those steps. I can't be a half a step up. I mean, try to climb a step ladder sometime 1/2 step at a time. You know, put your foot halfway up and then try to get your next foot up and see how far you go. Well, I'll tell you how far you'll go. You'll go to the nearest emergency room to get your shins taped up because you're not going anywhere and you're just going to keep going back to the same step. Now, I can take a big step and I can go here and then I can go back down 2 steps and 1 and go back to where I was. But again, I can be up there, I can be down here, I can be at the specific steps in between, but I can never be between those steps. That's the difference. An inclined plane, I could be halfway in between those steps. Because if I laid a board there, I could be any place between those. But in step fashion, I cannot be. And that's exactly what Bohr was saying. For some reason, the electrons in an atom have very specific steps that they can be in. They can't be in between anywhere else. So, accepting that, then Bohr designs his model to explain then the behavior of the electron, or the relationship of the electron to the atom. So Bohr says that we have then an atom with a nucleus, and we have very particular energy positions that the electron can be in. And he called these energy levels, or N. We sometimes call them shells, electron shells, they're sometimes referred to. As a matter of fact, in geochemistry and that, where they're talking about X-rays, they often talk about K, L, M, N, and O shells. We don't use the term shells anymore as far as chemistry is concerned. We talk about energy levels. So these are what we would call the principal energy levels. Like I say, the electron could jump from here out to number 5 and it could come all the way back. Or it might jump up to number 5, as we see over here, and then it might come back just 1 step from 5 to 4, or it might come back from 5 to 3, or it might come back from 5 to 2, or it might go all the way back from 5 to 1. The other important thing was that the electron never gets below this energy, which Bohr said there is a minimum energy that an electron can ever have. It never goes into the nucleus, it never disappears. This is the minimum energy, and this is referred to as the ground state. The ground state of the electron is the lowest energy position that it can get into. In the case of hydrogen, then, the ground state would be down here in this n equals 1 position. Now, Bohr then pictured the atom in what we call a planetary model, that the electrons were in these particular positions and that the electron was in fact orbiting around the nucleus just like the planets orbit around the sun, or the moon orbits around Earth. That's the way the electron was pictured. And based on the attractive force, remember hydrogen is quite simple, 1 proton, 1 electron, so we have only 1 charge to worry about. Based on the electrostatic charge, the energy of motion of the electron, centrifugal force, Bohr used those numbers, those frequencies, and was able to calculate the distance that the electron would be from the nucleus. Now, you might say, of what use is a model that is based on observation? A model should be able to make some predictions. Well, the interesting thing was that Bohr's model actually did allow him to predict that there were going to be another series of lines. The first series, of course, that he was looking at was the visible light series. He said there's another series of lines, another series of frequencies that we can't see, but should be there. And he calculated what the actual frequencies should be. Well, Bohr then went on with his planetary model to begin trying to predict the frequencies, the spectra that we should see for other gaseous elements like helium, oxygen, nitrogen, etc. Starting with helium, he found that his calculations didn't work. He could get somewhat close, but he could never get real exact. And the reason for this is that as soon as we go to 2 electrons, we have a problem, because now in addition to the electron being attracted to the nucleus, when we put a second electron in here, we have an electron-electron repulsion. And because we couldn't say where the electrons were at any instant relative to each other, it was impossible to put into the calculation the actual force of the electron-electron repulsion. And so when he tried to calculate the spectral lines for helium, it didn't work. However, if we took helium and put it through a ionizer like we saw that Thomson did with the neon in our previous lecture, where he found the isotopes of neon, if we put helium through, knock an electron off, and make a helium plus ion, now helium atomic number 2, when we take one of its electrons away and form helium plus 1 ion, we're talking about a 1-electron system. And when they did that, sure enough, Bohr could calculate exactly the wavelength or frequency of radiation that the helium plus ion should give off. So his model worked. His model worked to predict any system that had a single electron. Well, that's not very good because it doesn't go very far and you can't make single electron species anymore. Bohr was aware of that, but Bohr's major contribution was the fact that he said that there are only very finite number of positions electrons can be in. There is a minimum energy state called the ground state. Electron does not slowly spiral its way into the nucleus. It has some minimum energy and never goes below that. And so those were major contributions that Bohr made. Well, at least had some idea now relative to the relationship, but of course the model wasn't very complete nor very broad as far as talking about other atom behavior. And so we go next to a scientist by the name of Louis de Broglie, a Frenchman. And Louis de Broglie said every particle that is in motion has associated with it a certain wavelength of radiation. Whether it be a molecule moving, whether it be an automobile moving, whether it be a person moving, every moving object has associated with it a particular wavelength of electromagnetic radiation. And so what de Broglie was then saying is that we really don't need to define where the electrons are in terms of geometric position. What we really need to do is define the electron in terms of energy. And so he stated then that energy is equal to h nu. Didn't write that very good, h nu. H is a unit called Planck's constant, and you don't need to worry about this. And this is the frequency. What de Broglie was saying is, as the electron moved around in these orbits, it must have a certain wavelength associated with it. Now, it can only, we can only see its energy when, as it moves around, it is in perfect wavelength distance, so that as the electron comes around and returns back to where it was, that we're at an exact wavelength. So we're at that same dip every time we go around. If we get out in between here, it wouldn't be proper wavelength, and they would interfere and the energy would just not be there. We wouldn't see it. So the reason we observe only particular frequencies is because those are the only then wavelengths that are totally in phase relative to the electron's position and energy in the atom. And so de Broglie said we really don't need to worry about the distance from the nucleus and that. What we're going to say is that there are only certain allowed energy positions in the atom because there's only certain wavelengths where it will be totally in phase. And so he approached it totally from a different standpoint. Merely energy relationship, not worrying about the fact that it's a particle and that it would have a particular position. So this is sort of the next step in our model. Well, then we go on to a third person, and the major change then, a mathematician actually by the name of, well, physicist, mathematician, by the name of Schrödinger. Schrödinger, as a mathematician, then wrote a mathematical equation. And we talk about the Schrödinger equation. Wrote a mathematical equation to describe every energy position that should be allowed in an atom. This is whether we have 1 electron or 5 electrons or whatever the case might be. He said we don't need to worry about the electron being a particle. We don't need to worry about if it's moving in an orbit or if it's standing still or if it's moving in and out or goes around in a square. Doesn't make any difference. The only thing we're interested in is the energy. And so he developed, as I say, this mathematical equation called the Schrödinger equation, and took us then to a model which today we refer to as quantum, the quantum mechanical model of the electron in an atom. Now, the quantum mechanical model has 4 components to it in Schrödinger's equation. There were 4 numbers that are going to be plugged into the mathematical equation to solve for each allowable energy position in the atom. We first of all have what we call the principal energy level. That's designated by the letter N. Just a moment ago we saw even in the Bohr picture where we had n equals 1, n equals 2, etc. Those are the orbits. But Schrödinger is saying there are principal energy positions. Within the principal energy positions, there are actually some sublevels. And these sublevels are designated by the letter L, and they also depict the shape of the volume of space where an electron with a particular energy might be found. We're not saying its direction of movement again. We're merely saying that here's a high probability of where the electron will be if it has this particular energy. So the L term then is sometimes referred to as the number of energy sublevels within a principal energy level. Notice the numbers for the principal energy level start with n equals 1. That's the ground state. That's the lowest energy state in an atom. So there is no n equals 0. N equals 1 is the lowest energy. The sublevels relate to this, starting at 0 and have a maximum value up to n minus 1. So in other words, if n was 3, L could be 0, 1, and 2. Could have 3 values for L. Could have 3 sublevels of energy. All right? It's sort of like, again, if we think of it in terms of a hotel. We have floors, and if we think in terms of potential energy, or energy that it takes to get to a room at a certain level. Obviously, it takes more energy to get to the 4th floor of the hotel than it would the 3rd. But within the 3rd floor, we could have rooms close to the elevator, or we might have rooms way down at the end of a long hall. And if you were carrying a suitcase and had to go up 3 floors and down to the end of the long hall, that energy there that you've put in may be nearly as much as it would have been to get to the 4th floor. So now we're talking about the sub-levels within the floor of energy. Finally, because these sub-levels have certain shapes, and by the way, the term that we use, orbital, not an orbit. An orbit deals with the planetary model proposed by Bohr. An orbital is a volume of space in which electron can be found 90% of time. Now that means with a particular energy it can be found in that volume of space. So an orbital is then, it does have some physical shape to it. That's what we're talking about up here. And because it has some physical shape, it is possible it has some orientation, X, Y, Z, whatever case it might be. And the orientation number that went into Schrödinger's equation was given by the values of minus L, 0, up to plus L. By that I meant that if L was equal to 1, then we could have a minus 1, a 0, and a plus 1 orientation, which we could think of in terms of being like an X, a Y, and a Z orientation. So this tells us the sublevels. This tells us how those sublevels are oriented. Finally, if we accept that the electron is in fact a particle, and then we accept the fact that it's spinning, and experimental evidence indicates that that must be the case, then the electron, the little electron spinning around, has its own magnetic field. And because it does have, it can be aligned with a magnetic field or can be against the magnetic field. And so we talk about a plus 1/2 and a minus 1/2 spin to electrons. Now, let's advance this just a little bit here. Once again then, the principal energy level, n equals 1, 2, on up to infinity. Question?
Yes, is that infinity that's OO?
Yeah, that's supposed to be. Question was, is that little figure 8 laying on a side, that's infinity. Badly written, but that's what it stands for. All right, we go down to L. L is the number of sublevels. As a matter of fact, we can state that the number of possible sublevels in an atom is equal to the value of n. If n was equal to 7, the 7th principal energy floor, within that energy floor there would be 7 different sublevels, 7 different energy states within the primary energy state. So whatever the value of n is tells us then the number of different sublevels that are within that principal energy level. Now, when we go ahead then and we take, let's start first of all here, well, that's the relationship we saw before. If L is equal to 0, if we make a probability plot of all the positions an electron could be with that allowed energy, then we produce this volume of space, and it's called an s orbital. That's the name we give when L is equal to 0 numerically. We refer to the volume of space that the electron would be as an s orbital. if we want, we can take a look if we were to do a density plot, then we would have something that would look like that. In other words, the shading here represents where we would find the electron in that orbital. The orbital is the volume of space. And what we're seeing here is that close to the nucleus we seem to have a high probability of the electron being there, a little less out, but then again sort of out in this area we see again a greater density. Every one of those spots represents where an electron could be with that energy in that particular atom. But every one of those positions, every one of those dots is the same energy. We don't, in quantum mechanics, we don't say it's going in a circle. We don't say it's going anywhere. All we say is that it has a 90% probability of being somewhere in this volume of space at that instant if it has that energy. Now, if we plug in, then L equals 1 into the Schrödinger equation, we produce a new shape, and the new shape is called a p orbital, and it has sort of a figure 8 shape to it. And if we take a look at that plot, and this one will look more like a plot. If we were to take a computer and say, now plot all of the points where the electron can be relative to the nucleus with this energy in this mathematical equation called the Schrödinger equation, this is what we would get. This, of course, is a two-dimensional plot, but it would be a three-dimensional plot. And what we're saying is then that if we were to draw a shape and include 90% of those dots, now when we do this, we would do something like this. And so we get this figure 8, or sometimes called a dumbbell shape, to the distribution. This is called a p orbital. Now, when we have an s orbital, when we have a spherical orbital, and I'm going to put all of this up here now so we can look at it related to each other. When we have L equals 0, which gives us this spherical plot, if we go down here to our orientation number, m, if we put in m, we would have 0, 0, 0. All it means is that you can't orient a sphere. If I have a totally uniform colored ball, I can't tell which is top and bottom. It doesn't make any difference. There is no orientation to a sphere. However, if I have a dumbbell shape, like I do in the P position here, now I have a shape that I could tell which way it's pointing. And so if we take a look at M, once again, remember that's going to be the direction, the orientation. If I have L equals 1, I could have -1, 0, and +1. In other words, I can have 3 equivalent p orbitals, energy-wise, and they will be oriented in 3 different axes. So I can have 3 p orbitals, all with exactly the same energy. The only difference is their orientation. And so, here's what we see if we look at now the p orbitals oriented. In the second sublevel, when L is equal to 1, in that second sublevel, we can have 3 p orbitals. They would look like that. All right? Now, if we go beyond that, if we go to L equals 2 here as a new sublevel, we get what we call a d orbital. And if we make a plot for that energy, we get a new shape, different than either the s or the p. We'll get a totally new shape for this thing called the d orbital. And for that shape, we get there are actually 5 of them, and that goes back to M. Now, if L is equal to 2, that's what we were talking about here. We said L is equal to 2. That gives us a d orbital. These are d orbitals. And how many orientations could we have? Well, we would put it into M. And so M could have value of -2, -1, 0, +1, +2. It could have 5 orientations. And that's why we have 5 distinct d orbitals. These are, again, computer-generated or mathematically generated probability plots of the volume of space that would contain an electron with that particular energy in it. Now, if we had just one electron in this whole position, which is possible, then that electron could be in any one of those d orbitals at any time. All of those d orbitals are equivalent in terms of their energy. So there wouldn't be any preference to which one the electron was in. Or the same with the p's that we looked at just a moment ago. Now, if we go back once again, here then, to finally L equals 3, we get a new type of orbital that we call an f orbital. So we're going to have 4 orbitals really that we're going to look at relative to atomic structure and the periodic table. We're going to have an s orbital, we're going to have p orbitals, we're going to run into d orbitals, and we're going to run into f orbitals. Now the f orbital, L is equal to 3. So notice if we come down here in orientation, that means we have -3, -2, -1, 0, +1, +2, +3. There should be 7 then f orbitals. 7 f orbitals. All right? Now what would they look like? Well, they look pretty messy. That's all you can about say. I think I have a picture of it here. And you don't need to worry much about that. I don't expect you to reproduce these in drawings. But we have quite a variety. We have some that have 6 lobes on them. Notice here 6 lobes. Here's some that have 8 lobes on them. Each one of those represents now an individual f orbital. Each one of those represents an energy position that is equivalent. If we had one electron in an f sublevel, it could be in any one of those 7 f orbitals. All right? Now, the last thing we're going to say in terms of quantum mechanics from the Schrödinger equation is this concept right here, the S, the spin. Each orbital, an S or a P or a D, each individual orbital can contain 2 electrons in that same volume of space. Theoretically, they could be in identically the same position because we're only talking in terms of energy. So, can contain 2 electrons provided the 2 electrons have opposite spins. In other words, we can put 2 electrons in. If one is spinning this direction and the other is spinning this direction, we can put both electrons into the same volume of space then. And looking at the spin of the electron then, this is what we're talking about right here. So that within a magnetic field then, the electron could be aligned so that, notice, the south pole is with the south pole and the north pole with the north pole. That's higher in energy. If you've ever tried to put 2 magnets together and put 2 north poles together, what do you find? They kind of repel each other, don't they? If you put a north and a south pole together on a magnet, they attract each other. Okay? So what happens, in order for the electron to be oriented in this fashion, south pole of it to the south magnetic pole, that's going to be higher in energy. That's why it's called plus 1/2. Then this one over here, where we have the south pole of the electron pointing towards the north pole of the external field. That's lower in energy, and that's why it's called minus 1/2. Now, we really don't care in most cases whether we're talking about the plus 1/2 or the minus 1/2. The fact is that we can put two electrons into one individual orbital in the atom, provided they have opposite spins. That's all we have to worry about, not which is up and which is down in terms of energy. Now, let's, well, maybe, there we go. Let's just take a kind of a look in terms of what we're talking about then relative to principal energy levels and then these sublevels. When L is equal to 1, when N is equal to 1, we can have only one sublevel. Remember, the number of possible sublevels is equal to the numeric value of N. We can have only one sublevel. That sublevel is called an O, or 0. That's the value for L. And we said that when L is equal to 0, what type of orbital do we have? An s orbital. How many are there? Just one. How many electrons could we put in that? 2. So the first sublevel of an atom, any atom, can have only 2 electrons in it. That's all. First sublevel, well, actually the first principal energy level, I should say, because it has only one sublevel. The first energy level in any atom can contain only 2 electrons. There's only one orbital. If we look at the periodic chart, notice that the first row of the periodic chart contains how many elements? 2. Isn't that odd? No, it's not odd at all. It exactly fits what we're saying, that the first 2 electrons that go into an atom in the ground state, we have only 2 positions. Once we go beyond 2 electrons, we have to start a whole new floor, a whole new energy level to get the 3rd electron in. And when we start that next energy level, we start another row in the periodic chart. Now, if we look at that second one, now, N is equal to 2. We can have 2 different sublevels. One of the sublevels will be an S when L is equal to 0. The other sublevel will be a P sublevel. How many S's can we have? Just one. How many P's can we have? We can have 3 P orbitals, 3 orientations. How many electrons can an S hold? Just 2. How many electrons can a P hold? Well, there are 3 orbitals and each one can hold 2, so it could hold 6. So how many total electrons could I put into the second energy level of an atom? 8. 8 electrons. How many elements appear in the second row of the periodic table? 8 elements. It's maybe odd, but that's why the elements fall the way they do, is because that's the way the electrons fall in the individual atoms. Well, we can see then just quickly, when N is equal to 3, we're going to have 3 sublevels, an S, a P, and a D. And S can have only 1, the P can have 3, the D can have 5, and each can contain 2 electrons. In our next lecture then, we'll come back and talk about putting electrons into what we call energy orbital diagrams. And I'll just put this quickly here. So we're going to take this and now put the electrons in to explain the similarity of elements and the dissimilarity of elements and their chemical behavior.